In this video, we're going to look at the types of reactions that chemists have been able to classify the thousands upon thousands of individual reactions, recognizing that there are patterns that are followed, and all of these thousands of reactions fall very naturally into these 5 categories. And in this video, we'll discuss each of those. We'll look at what the features are for each of them and show you how you can predict products of reactions once you know which type of reaction a particular example fits into. The first that we'll look at are reactions that we call synthesis reactions. So you can see that we're going to have some substance A, it could be an element or a compound, is going to react with another substance, an element or compound B. They'll come together and they're going to form a single product AB. So, key factors to remember about synthesis or combination reactions, you can also use that term. First, you're going to have 2 or more substances that come together to form a single product. Second, often as these bonds are formed to form this product, some energy will be released. And something you have to contend with now and again, if nonmetals are involved, because they tend to form covalent bonds, it can be difficult to predict what the product will be. So keep these 3 things in mind as we look at the examples ahead. In the first one, we've got aluminum metal reacts with oxygen in the air. So I know aluminum is a metal, so aluminum symbol is Al, it's a solid, it's reacting with oxygen, and I remember that oxygen is one of my diatomics. This looks like a synthesis reaction because I've got 2 elements combining with each other. So aluminum will join up with oxygen. I have to come up with the correct formula. I follow the same pattern I have followed for the last several weeks. I look at their oxidation states, 3 plus for aluminum, 2 minus for oxygen. So I know that aluminum oxide is Al2O3, and oxides are going to tend to be solids. Once I've got my correct formula, I don't need those charges anymore. There's my skeleton equation. Now I'm going to go and balance this, and I can see that to get the oxygens to equal each other, I looked for the common factor between 2 and 3, which is 6. So to get 6 oxygens on the left, I put a 3 in front of the oxygen molecule. And to get 6 oxygens in the products, I put 2 in front of that aluminum oxide. Now when I did that, though, that obviously changed aluminum also. I distribute the 2, 2 times 2 is 4, and that's why I put a 4 as my coefficient in front of the aluminum on the left-hand side of my equation. There is our balanced equation for aluminum reacting with oxygen. Now let's look at our second example, sulfur trioxide. Well, obviously this is a covalent compound. I remember my prefixes, SO3, and it's reacting with moisture. Obviously that's water, H2O. This one, a little difficult. It's hard to predict what the product would be, but from my experience, these guys are probably going to come together, and if I look carefully, this is one of the key problems with acid rain. It's actually going to form an acid, in this case, sulfuric acid, H2SO4. I checked the left side and the right side, and I noticed that this skeleton equation is already balanced. So there's my second synthesis reaction. You can see in the second one, a little more difficult when you've got compounds interacting. I had to rely on some experience and some extra knowledge I knew about sulfur trioxide and acid rain. Now let's look at a second type of reaction, and these are called single replacement reactions. In these, you'll have an element, in this case C. In this first example, I'm assuming that C is a metal. And so I've got an element potentially reacting with an ionic compound. And the thing is, C, if it's a metal, can only replace another metal. And I know that metals or cations are listed first in my compounds. So if C is going to replace anything, it will try to replace A. And if it does, C now has joined up with B, and A has been pushed off of the compound and is now free. On the other hand, if C is a nonmetal, then it can only replace another nonmetal. Again, you remember that nonmetals are listed second in ionic compounds, and so if it's going to replace anything, it can only replace B. And so now C takes the place of B with bonding to A, and B has now been released and is alone. Let's look at a couple key things that I want to highlight for single replacement reactions. First of all, replacement simply means atoms of an element will replace atoms of another element in a compound. As you've seen in my general equations, a metal can only replace a metal, and a nonmetal can only replace another nonmetal. But this doesn't automatically happen. When you go to your tables folder, you'll find what's called an activity series. To make a determination whether a metal can replace a particular other metal or a nonmetal replacing another nonmetal, you need to reference that activity series. Let's look at a couple examples and see how this plays out. Here are my two problems. In the first one, I'm going to have aluminum metal dropped into a beaker that has a solution of lithium nitrate in it. So let's write the formulas. You've got aluminum, again, is a metal, and so it's in the solid state. I have to write the right formula, correct formula for lithium nitrate, and I know lithium is 1+, it's an alkali metal. I know nitrate is a polyatomic ion, it's a nonmetal, it's 1-. Clearly I have the correct formula, LiNO3. It's a solution, so I put the AQ. So I recognize I've got the circumstances where this could be a single replacement reaction. However, I have to check to see if aluminum, a metal, can replace lithium. Remember, metals are listed first, so lithium's the metal. I'm going to look for those two elements on my activity series. And so aluminum trying to do the replacing must be more reactive than lithium. But when you look at that table, you will find aluminum is well below lithium. So in this case, aluminum cannot displace or replace lithium, and therefore, when I drop the aluminum into the beaker, nothing is going to happen. There will be no reaction. So you can see with single replacement reactions, you actually have to make a decision as to whether something will take place or not. In this case, nothing happens. Let's look at our second example, see what that leads us to. We've got chromium, again a metal, so it's a solid. Stannous chloride, I look up stannous, I know that means it's 2+. Chloride's a halogen, that's 1-. I have to come up with the right formula, SnCl2, and it's a solution. Again, let's erase the charges. Chromium is trying to replace tin, and this time, when I look on my activity series, I see that chromium is higher up on that chart than tin is, and therefore chromium is more reactive, and the chromium pushes the tin off. Tin is a metal, it's going to be in the solid state. I got to check that formula though for the chromium chloride. I look at the oxidation states, and I see that I'm going to need 2-chlorine. Now in this case, I didn't stipulate what chromium could be. It can be either 2+ or 3+. I made it easy on myself. I decided to just use 2+, and that's how I get my formula, CrCl2. I look on my solubility chart, and I notice it is soluble in water, so I put AQ. So we've got our two products. You notice again, I had to make a decision using my activity series as to whether this would really happen or not. I look at this scaling equation and I notice that it is already balanced, and there's our final equation. So the key thing with single replacements, you've got an element interacting with a ionic compound You have to reference your activity series to see if the element trying to do the replacing is capable of doing that. If it is, the reaction happens. If it isn't, then nothing will occur chemically and no reaction occurs. Let's go to a third type of chemical reaction, and these are called double replacements, and we've already talked about these, so this should be really familiar to you. You have two ionic compounds in solution usually, and essentially the double replacement comes from the idea that either the cations or the anions, doesn't really matter, essentially are trading partners. So here you can see I have A and C trading their partners. A is going to hook up with D, C is going to hook up with B. Remember, cations are always listed first, and these are the potential products. The key feature for recognizing that you have a double replacement reaction is if you have two ionic compounds being mixed. Now, these don't automatically happen. It's not a given just because I can move letters around on the page. Let's look at the features for double replacement reactions. First of all, you have an exchange of ions, so they trade partners. This is usually going to happen in aqueous solution because these ions have to be free to move around and be able to hook up to something new. Now, what are the criteria? What has to happen? Well, the first one we've seen already in a couple of different labs. One possibility is you get one of your products and it's a solid. It's insoluble. You check your solubility chart. It forms a solid. The solution turns cloudy. I know I have a precipitate forming. That's one possibility. But there's a second possibility. We saw this in one of your labs. A second possibility is you get a gas forming. Bubbles would start to form. We saw this in your lab where you had the giant grid and one of your combinations, in fact, led to the formation of a gas. You saw bubbles form. That doesn't have to happen along with the precipitate. It's a second possibility. And then you have a third possibility. One of the products is water forming. So these are three possible products. Only one of these three has to happen. More than one might happen, but usually only one of them will occur. And at least one must happen for the reaction to really happen. Let's look at a couple of examples and see how this plays out. So I've got these two examples. The first one, hydrogen phosphate solution mixed with lithium hydroxide. So let's write the formulas for those two. We go to our oxidation states. 1 plus for the hydrogen, 3 minus for the phosphate. So hydrogen phosphate is actually H3PO4. It's a solution. We put AQ. And of course, after we're done, we erase the charges. Lithium hydroxide. Lithium is 1 plus, group 1. Hydroxide's a polyatomic, 1 minus. We've already got the right formula. It's a solution, AQ, and let's erase the charges. All right, so it looks like the circumstances for double replacement reaction happening, two ionic compounds. So they're going to trade partners. That means hydrogen and lithium would switch partners. So hydrogen will go hook up with hydroxide. I've got to get the right formula. I look at the oxidation states. They already match. HOH is going to be my formula, but I recognize right away, of course, that that really is H2O, and that's a liquid. So I've already met one of my criteria. I got water to form when the ions traded places. I have to track down that other product, lithium hooking up with phosphate. I look at their oxidation states. Again, it's my job to come up with the right formula. They're not matching. I need 3 lithiums. I look at the solubility chart. In fact, this is soluble. So if we had not had water formed, the reaction would have happened, but we met one of the 3 criteria, water forming. Now I balance the equation. I see 3 lithiums, so on the right side I'll put a 3 in front of the lithium hydroxide. Let's see, that gives me 3 hydrogens in the first term and 3 hydrogens in the second term. On the left, that's 6. So I put a 3 in front of the water to get 6 hydrogens. And if you just double check your phosphorus, 1 each on each side, 7 oxygens on both sides. This is balanced. So they traded places. It was a double replacement reaction. My second example, boron nitrate. I look up the charges, the oxidation states, and I see that I need 3 nitrates. And it is a solution, so I put AQ. And again, let's get rid of those charges. I go to my second reactant, potassium sulfide, oxidation states of 1 plus and 2 minus. I'm going to need 2 potassiums. It also is a solution. And again, let's wipe away the charges. You can see I've got the circumstances that this might be a double replacement reaction. 2 ionic compounds in solution. The ions are going to trade places. Boron is going to trade places with potassium. So boron hooks up with sulfur, potassium with nitrate. Again, though, we've got to write the correct formula. So let's look at the oxidation states. 3 plus for boron, 2 minus for sulfur. So boron sulfide is B2S3. I look on my solubility chart. It turns out to be a precipitate. It's insoluble. So I've met one of my criteria again. I know this reaction will happen. Double check the potassium nitrate. See if that's the right formula. I'm all set. Don't have to change the subscripts. I check the solubility chart, and it is indeed soluble. So I met one of my criteria. I got a precipitate. Now we want to balance this. I see 3 sulfurs on the right side, so I'll put 3 in front of the potassium sulfide. When I did that, I also wanted to take care of the boron, 2 on the right side, so we'll put a 2 in front of the boron nitrate on the left side. Now I've got 2 times 3, 6 nitrates on the left. Let's put a 6 in front of the potassium nitrate. And then that changed the potassium to 6, but I already had 6 on the left side, so now we're good. There's my balanced equation. All right, so double replacements aren't always going to be precipitation reactions. Many times they will. There are other possibilities, so you can see we're expanding the kinds of reactions we'll run into. All right, let's go to a fourth type. This looks a little bit like the synthesis reaction in reverse. We're going to have a single compound, and it's going to start to break down into its components. That's why we call it decomposition. Now, there's some features for these. First of all, you need energy to break those bonds. So some kind of energy is being added. It could be heat, it could be a flame, it could be light. Something's got to break those bonds. Sometimes it can be hard to predict the products if you're not familiar with the different possibilities. However, if it's binary, if it's a binary compound that has only 2 elements in it, well, then it's easy. It's going to break into those 2 components, its constituents. Let's look at a couple of simple examples. The first one, we've got a beaker of water, and we're going to shoot some electricity through that. So obviously we've got H2O as a liquid. We're going to shoot some electricity in it. We got a binary compound. It's probably going to decompose, and we'll get the 2 components. But be careful. I got to remember that both hydrogen and oxygen are diatomic, and they're both gases. So when this happens, I would actually start to see bubbles forming in the water. Some of them will be hydrogen around one electrode, and others will be oxygen around the other electrode. And then simply I've got to balance my skeleton. I see I've got 2 oxygens on the right, so I'll get 2 waters on the left, which then altered the hydrogen, and so I put a 2 in front of the hydrogen on the right side. Let's look at a second example of a decomposition. In this one, we are going to take some mercury 2 oxide powder and putting it into a test tube. We're going to heat up that test tube. So the mercury 2 oxide, 2 plus for the mercury, 2 minus for the oxygen, so HGO, and of course it's a powder, so solid. Let's erase those charges. We're going to heat this up. It's a binary compound. That means it's going to break into its 2 components. Mercury is a liquid, one of those elements that's a liquid at room temperature, And oxygen, remembering it's diatomic and it is a gas. And then once I've got my Skellen equation, I simply come in and I balance it. And there we go. Okay, decomposition reactions. Some kind of energy has to go into the system in order to start breaking down those bonds and breaking down that molecule. All right, our fifth and final type of reaction, these are called combustion reactions. Combusting means to burn, so things have to burn. And in most situations, when we are combusting materials, in everyday life, in our world, we get energy frequently from combustion reactions, and that involves taking what are called fossil fuels or hydrocarbons and burning them. So all the different things we get from oil, we're going to burn them, and we're going to retrieve the heat, we're going to capture that heat and make it do work for us. And of course, to burn something, you need oxygen. Without oxygen, combustion will not take place. In this generalized equation, you can see that if we fully burn the hydrocarbon, you'll get two products, carbon dioxide and water. Let's look at the features of combustion reactions. First of all, of course, you need oxygen. So a lot of times when we're fighting fires, we try to eliminate oxygen and the fuel will stop burning. Be careful. Oxygen itself is not a fuel. Oxygen helps fuels to burn. Secondly, often in combustion reactions, the fuel will end up being a hydrocarbon or a fossil fuel. If you have enough oxygen mixed in with the fuel, the combustion will be said to be complete. And if you burn a hydrocarbon completely, it will break down into two substances, carbon dioxide and water. However, if something restricts the amount of oxygen that can mix in with the fuel, then you'll start to get incomplete combustion. And you get all sorts of different products depending on how complex the hydrocarbon happens to be. But some of the products are worrisome, and one of the key ones is obviously carbon monoxide, a poison, dangerous gas formed. You'll hear about this. We're into the fall-winter cycle where people are heating their homes, and very frequently you're reading stories about carbon monoxide poisoning, and it happens because of incomplete combustion. Let's look at a couple of examples here then of combustion happening. The first one, we're going to take some glucose, sugar, produced by plants, and it says it's going to undergo complete combustion. Well, glucose, if you look it up, its formula is C6H12O6. We're told that this is going to get ignited, so there must be oxygen present, otherwise it wouldn't burn, so you have to know to put oxygen in as one of your reactants. And since they said it was complete, and I've got a hydrocarbon burning, I'm only going to get CO2 and water. And there's my Skellen equation. And again, balancing these, you should be pretty much pros at this point. I'll go after the carbon first. I need 6 carbons on both sides. I went after the hydrogen. I wanted 12 on both sides. We'll leave the oxygen to the end. I've got 12 from the first term on the right side. I've got another 6 on in the second term for a total of 18. On the left side, then my first term, I don't want to change that. So I've already got 6 oxygens nailed down in that first term. I need 18 total. I've already got 6. That gives me 12 left. I'm going to get them both, all of them, all 12 from the second term, and that, of course, calls for 6 there, too. Okay, there's your balanced equation, 1, 6, 6, 6. Let's look at a second example. We've got this larger molecule. It's going to undergo combustion. Again, it looks like a hydrocarbon. So it should burn. It says it's going to combust, so we're going to add oxygen in. And they reference that it's complete, so again we get CO2 and water. So there's my Skellen equation again. Okay, now we're going to balance this. Again, we're going to leave oxygen to the end. We go after the carbon, 18 on the left side, so put an 18 in front of the CO2. Go after the hydrogen, I've got 36 on the left side, so let's put an 18 in front of the water. Then finally, we'll take care of the oxygens, 36 from the first term on the right side, 18 from the second term, gives me a total of 54. I need 54 on the left side. I've got 2 in the first term. Okay, I've got that nailed down. I don't want to have to change that term. So I've got 2 nailed down, 52 to go. And of course, that means it's going to be a 26. And there you go. Those are the 5 types of chemical reactions: synthesis, decomposition, single replacement, double replacement, and combustion. Hopefully, these examples and my explanation have helped you to better understand them.